Hello, my name is Atul, student code PCM25406. I am a student at CEPT University, pursuing my Masters in Construction Engineering and Management. This presentation is a part of the studio titled Construction Project Formulation and Appraisal. Today, I will be presenting a complete formulation of a construction and demolition waste recycling plant project developed for the Ahmedabad Municipal Corporation. This presentation is structured into 10 sections covering each a key layer of decision making, design, planning, and management. Ahmedabad generates nearly 1,000 tons of construction and demolition waste every single day. Most of this material either ends up in unauthorized dumps scattered across the city or mixed with municipal waste. The project aims to address this rapidly growing challenge by establishing a scientifically designed C&D waste recycling plant that can process 1,000 tons per day and convert it into usable outputs like recycled aggregates, manufacturing sand, and other building materials. The brief also situates the project within the broader framework of sustainability, reducing landfill pressure, conserving natural resources, and promoting circular economy practices. The plant is envisioned not only as a processing facility, but as an essential urban infrastructure component that improves the city's material flow, environmental performance, and long-term resilience. This project therefore combines engineering, planning, sustainability, and financial logic into one integrated solution. The design brief focuses on creating a function-driven industrial ecosystem rather than an architectural object. The master plan divides the site into 13 functional zones, separating waste intake, inspection, primary processing, secondary processing, storage, vehicular circulation, and dispatch areas. The zoning ensures there are no cross flows between incoming waste and outgoing materials, reducing congestion and increasing safety. The landscape design uses native, pollution-tolerant species that control dust, absorb noise, and stabilize the microenvironment. These green buffers are not only decorative, they support air quality, worker comfort, and compliance with environmental regulations. Environmental safety provisions include designated hazard zones, setback requirements, stormwater strategies, and controlled access points to ensure safe operations around heavy machinery. The electrical design explains how the plant runs on a combination of transformer power, DG backup, and solar PV. The electrical loads are high due to continuous crushing, screening, cleaning, and washing. To maintain stability, the design includes capacitor banks, power factor correction, and a well-planned HT distribution system. Together, these elements make the entire system robust, safe, and operationally reliable. The section highlights the backbone services that ensure uninterrupted plant operations. The rooftop PV system offsets a significant portion of the plant's daytime demand, reducing dependence on the grid power and lowering operational cost. The system is designed with inverter protection, anti-islanding, and load balancing to ensure reliable integration with the electrical network. Water supply requirements are carefully calculated for washing, dust suppression, equipment cleaning, and domestic use. An efficient water recycling loop reduces freshwater demand, lowering OPEX while supporting environmental goals. Fire safety is designed according to the industrial codes with hydrants, extinguishers, safe shutdown provisions, and clearly marked emergency routes. Fire zoning and equipment placement are customized for area with machinery heat, diesel storage, and electrical panels. Finally, site infrastructure includes internal roads, stormwater drainage, street lighting, utility corridors, etc. These elements are often invisible in drawing, but make a huge difference in operating efficiency, enabling continuous movement of trucks, easy maintenance access, and safe nighttime work environment. The client's work breakdown structure outlines all responsibilities held by the AMC, the Ahmedabad Municipal Corporation, before the EPC contractor enters the picture. This includes pre-feasibility studies, waste characterization, site confirmation, environmental considerations, financial approvals, and statutory clearances. The client's role is heavily front-loaded because decisions taken at this stage shape all the downstream outcomes. The methodology explains how the entire project was decomposed into manageable parts. Work was grouped first by phase: planning, procurement, engineering, construction, and O&M, then broken down by discipline. This structured approach eliminates ambiguity, clarifies dependencies, and builds a foundation for scheduling, costing, and risk management. A well-formed WBS is critical in public projects because it acts as a contract backbone, the schedule backbone, and the cost backbone simultaneously. Once the client establishes the project framework, the EPC contractor assumes responsibility for procurement. The WBS breaks this into systematic steps: identifying consultant requirements, preparing technical specifications, floating tender packages, evaluating submissions, negotiating terms, issuing work orders, and tracking deliveries. The EPC contractor also procures all plant machinery: crushers, screens, conveyors, washing units, dust suppression tunnels, and automation systems. These packages must be selected with precision because the plant's performance depends heavily on equipment compatibility. By structuring procurement into well-defined sub-packages, the contractor ensures that delays, mismatches, or cost escalations are minimized. The procurement WBS ultimately strengthens the supply chain reliability, reduces interface conflicts, and ensures readiness in construction. The engineering WBS translates the concept into coordinated construction-ready drawings. It spans process design, civil and structural engineering, mechanical layout planning, electrical distribution, MEPF integration, stormwater design, energy modeling, sustainability strategies, and safety planning. Engineering is sequenced so civil works are aligned with machinery foundations, electrical loads match equipment demands, and utility routes do not clash with structural members. This reduces rework, which is both time consuming and expensive, and ensures that the entire system behaves as one cohesive unit. Good engineering coordination directly influences construction quality, schedule performance, and overall plant efficiency. The construction WBS breaks execution into civil works, building construction, pavement and road drainage, electrical and mechanical installation, testing and commissioning. Activities are sequenced to support equipment placement, wiring, cabling, utilities, roofing, and enclosure works, ensuring smooth progress on site. Following construction, the O&M WBS defined how the plan will be operated for a 5-year period under the EPC contractor. Tasks include daily machinery checks, scheduled maintenance, water and energy management, product testing, worker safety protocols, and compliance monitoring. This structure guarantees performance continuity, smooth transition, and high uptime once the plant becomes operational. The project baseline outlines the full 604-day timeline from September 2025 to April 2027. Activities are organized phase-wise, mapped against the critical path. The baseline reveals that the EPC contractor controls most of the time-sensitive tasks, especially engineering, procurement, MEPF integration, and commissioning. Because float is minimal, any delay in design approval, equipment delivery, or civil readiness immediately affects the final handover date. The baseline reinforces that the schedule discipline, interface coordination, and proactive risk management are essential across the project. This section explains why the project uses a mixed contracting strategy: QCBS for the feasibility consultant, PMC and PMC because early stage work requires competence and analytical skills. The EPC contractor, however, is selected using the L1 system, which ensures cost control once design and specifications are fixed. This multi-layered structure spreads risk across different agencies and avoids over-dependence on a single contractor. The contract flow also enhances transparency, accountability, and regulatory compliance. Together, these strategies ensure that technical decisions, financial discipline, and operational reliability all remain balanced. The conclusion ties together the technical, managerial, and sustainability elements of the project. The plant is positioned as a critical infrastructure asset that supports waste management goals, reduces environmental burden, and produces valuable recycled materials. Through its structured WBS, the disciplined procurement, integrated engineering, and tightly planned baseline, the project demonstrates how a complex public facility can be delivered with clarity and confidence. The overall approach ensures that the plant is not only feasible to build, but also efficient to operate, maintain, and sustain over a long time. Thank you.